Yeah. So I posted an announcement for this, but just a quick shout out. So winter transfer fair is going on right now over at Pub. If you're setting up to transfer to university in fall and you don't have all the details figured out, especially if you're going to one of these schools, right? You can hop over there after class if you got time, and people from those schools will be there to help you out. If you're WSUV and we've already talked and so on, you're probably in good shape. But that's going on right now. All right, questions? Yeah.
Two questions.
Okay.
My first one is when I'm taking out all the traverse things, it keeps coming out like 0, and I'm not 100% sure why that is. And I've tried like many things to change it, but it still won't go away.
Okay. If you print an empty tree, does it print a 0?
Yeah.
Interesting. And you don't have a sentinel node, right?
No. I initialized it in the beginning, but I just set it.
What do you initialize the root to? Because without a sentinel, you should be able to initialize it to null, and that should be your empty tree. If you do a malloc, then you're going to have a node with a 0 in it.
Right, it's called the malloc. I think that's the reference null.
Yeah, so a truly empty tree. What are your nodes called? Struct node?
Yeah.
And what's your root called? Root. That's how you can create an empty tree. All right, so that's actually null. And then if you try to traverse it, your traverse code says if a null return, it shouldn't print anything. If you've been doing this by initializing root to a malloc, you may break a bunch of your code by doing this, right? So make backups, save copies, work on a copy. But this would be the way we do an empty tree. And then when you insert, right, for example, when you insert, you say root equals insert root number, or root equals delete root number, right? That's how you go from being non-null to being, from being null to being non-null. Second question.
It's about frame the memory. Which traversal would be like that?
What do you think?
I don't know what it's called, but it's probably the one that goes from like bottom to
Depth first?
yeah.
So depth first. We got 3 orders for depth first. So we got pre-order, we got in order, and we got post order.
Yeah, I used left, right, now.
Why did you choose that one?
Because it would get rid of everything on either side before it got rid of the node that you're
Cool. So left, right, note, post order traversal, right, says, okay, I'm going to traverse this tree. First, I'm going to visit everything here. Then I'm going to visit everything here. The last thing I'm going to visit is the root. So if you free instead of printing, this is a really good way to do it. Because it basically says free everything in this subtree, free everything in that subtree, and then free that one root. And at that point, you've already taken care of everything that was hanging off that root. So yeah, I would do left, right, note for freeing memory. Delete questions? Or let me rephrase, are there still questions about deletion?
It works with blank code.
Awesome. I took a picture of your code on the board in the hallway. I'll use that in future classes. So yeah, remember when you delete, you've got basically 3 cases to worry about. If we're deleting the root, right? We've got the totally general case where we've got some largest value in the left subtree, and it's got some previous which is also in the left subtree. And the goal is to turn largest into the root. So let me call this root. And so what do we want to do? We want to say something like previous right, and there might be stuff over here on the left of largest. So previous right can adopt what largest has on the left. So that sets up this, so we don't lose those nodes. And then we want largest to be the root, so largest left can point wherever the root left is, and largest right can point wherever the root right is. So now largest is pointing to this stuff on the left, it's pointing to that stuff on the right. Largest is now also the root of the tree. And then we can free the root and return the root of the new tree, which is largest. So that's your general case. An edge case, this is still our root. This is our largest here, and we got stuff hanging off here, but there's nothing to the right of this node. And we can't use this code over here because we don't know what previous is. If previous is your root, this is going to do all kinds of weird things, right? It's going to create a cycle on you if you work through it. So in this case, really all we want is largest right equals root right. So it adopts all this stuff, and then free the root and return largest. And your third case is where you've got a root and there's nothing on the left. So you got a 40 up here, there's no data to the left at all. So we don't have any of these cases. And in this case only, we really want to do something like temp equals root right. So find whatever that first node is on the right, free the root, and return temp. So this case where there's nothing on the left, the way we delete the root is just by treating the thing on the right of the root as the new root.
In your first case, is there a difference between setting the largest on the left or the smallest on the right?
They will both succeed in deleting. One will succeed in getting you points, the other won't. So for the assignment, you got to do the largest on the left.
Yeah.
But in practice, you might alternate. Every time you delete, do it from the left, do it from the right, to try to sort of help keep the balance. Or you might do some analysis and find that one requires less work than the other, but they're equally valid in general, just not in PA4. So if you're seg faulting or you're seeing loops where you print your traversal and it prints forever, most often what I'm seeing is this case right here, and it's not being treated as a special case. It's trying to use this code. And so whatever you're doing in your code, make sure, if you're doing this stuff, that previous and largest makes sense. Right, so that whatever code you've written, the effect is the previous node adopts the largest node's left child. Largest picks up the left and right subtrees as its children, and then this gets returned as the root of the tree. All right, good. So we've been doing heaps, and you've built heaps, you've inserted, you've deleted, you've up-heaped and down-heaped, and yesterday we heapified, so we took a sort of random heap-shaped collection of data and turned it into a heap. And we did this in a way that was order n by following a heapification algorithm. What I want to talk about today is how we implement these things in code. Because if we implement this with a regular binary tree, it's kind of tricky. Moving from a node to its left or right children is easy. We do that all the time. It's just root arrow left, root arrow right. Finding your parent is really hard unless you build back pointers. And we can do that. We can add one more piece to our structure called parent. And if we want to find our parent, we just follow that link. So now if we want to say, okay, does our parent satisfy the heap property, we have a way to get to that parent. What's still really hard, though, is you have your heap, and it looks something like this. How do we know where the leftmost position on the bottom row is? Right now we would start from the root, we'd move to the right, and then we'd come down to the left. But if our tree looks like this, the leftmost position on the bottom row we get by following 3 links to the left and then going to the right. And there's not a good way to sort of keep track of what this last position is. We could have a pointer saying, okay, right child of this node, that's the next position. But once you fill something in there, how do we know that the left child of this node is the next position? And so you can start at the root and you can do some kind of traversal algorithm, but that's not very efficient. So it turns out we can do everything we need to do with heaps without ever using pointers, without ever using mallocs, without ever using left and rights and parents and all of these things. And so we're going to implement this using nothing fancier than a plain old array. So let me make a heap over here. And let me make an array. And I'm going to store the indexes. I'm going to write the indexes of the array up here. And I'm going to store the elements of my heap into this array successively, starting at location 1. And I'm never going to use location 0. So let's just fill in this table of nodes and indexes and children and indexes. So let's start with node A. What's the index of node A in our array? Okay. What is A's left child? That's a B. What's the index of B? Okay. Let's look at node B. That's index 2. What's B's left child? D, which is index 4. Node C is index 3. What's C's left child? F, which is index 6. Do you see a pattern? Let's add a few more.
Are on the right, and even ones are on the left.
Odd ones are on the left, or on the right, even ones are on the left. So let's look at node D. Node D is index 4. Its left child is H, which is index 8. So if you had to hypothesize a formula for the index of the left child of a node, what might it be? Index of the parent times 2. And in fact, that's exactly correct. So left child left index equals parent index times 2. So right child of A is C, right child of B is E, right child of C is G, right child of D is I. And these have indices 3, 5, 7, and 9. So what's a possible formula for the right index? Parent index times 2 plus 1. So we have a way to move from a node to its children without having to use pointers. If we know the node is stored in an array at index position 4, its left child is guaranteed to be at position 8, and its right child is at position 9. And if I has a left child, it's going to be at location 18. And if that node has a right child, it's going to be at location 2 times 18 plus 1, 37. And so with a simple multiplication and possibly an increment, we can move down this heap from node to node, and we don't have any pointers anywhere in sight. All we need is indices. Now I can keep an integer variable called last, and I can set that equal to the index of the last thing in this heap. Okay, so if I want to find the root of my heap, what's the index of the root? Always at the index 1. So if I call this, h bracket 1, that's the root, guaranteed always. And if last happens to equal 0, that means my heap's empty, because I got 0 things in there. Otherwise, root bracket 1 is or heap bracket 1 is the root. So where's the last thing in my heap? What's the index of the last element? It's just last, right? So if I want to find the rightmost entry on the bottom row, it's just h bracket last. If I want to add something, I increment last, and I store at that location. And there I just added a new thing to my heap, and I've still got the heap shape. And if I want to remove the rightmost entry on the bottom row, I just grab the thing stored at this index, and then I decrement last. So finding the root, single operation. Finding the last thing, single operation. Adding a new thing at the bottom or removing the last thing on the bottom, single operations. Moving from a node to a left or right child, single operation. What about moving up? How do we find our parent? So h is node 8. How do we find h's parent d, which is index 4?
Divide by 2.
Divide by 2. F's parent, 6 divided by 2 is 3. D's parent, 4 divided by 2 is 2. And so on. What about these cases? I is equal to 9. Subtract 1 and divide by 2. And it turns out, if we do integer operations, we don't even need to subtract 1. If we just take child index and divide by 2, if that index happened to be odd, it'll basically give us index minus 1 divided by 2, because it'll round down. It'll throw away the 1/2. So if we take a node's index and divide by 2, we get the index of the parent. And if we take a parent index and we multiply by 2 and possibly add 1, we get the left and right children. So upheaping and downheaping, comparing a node to its children to see if it satisfies the heap property, nothing more than a little bit of integer arithmetic. And you can do this in assembly language. We can multiply by 2. How do we multiply by 2 in assembly language?
Rotate left.
Yeah, if you move a number to the left 1 bit, that multiplies it by 2. How do we divide by 2 and round off?
Rotate right.
Move it to the right. Right, and if there happened to be a 1 there, it subtracts the 1 basically and then divides by 2. So this is just a couple of shift operations or rotate operations. But we can do everything we need to do to implement a heap like this. Up heap, down heap, testing the heap property, moving things to and from the root, to and from the last position, and it's all just integer index math. So if you want to do a heap sort, and you know you have n pieces of data, you do one big malloc in the beginning to make an array. You load your data in and stick it in locations in the array, and you set your last variable to know where the last thing is, and then you do a heapify algorithm. So you start from the last element and you move forward and you check the heap property, and it's really fun to write actually. I strongly recommend it if you're like looking for a break. It's actually really fun to code this up, because you've been doing pointers for like 9 weeks now, and this is just like good old 121 stuff. All right, questions about that? So that's pretty much heaps in a nutshell. All right, so let's move on to the subject matter of PA5, which is dynamic programming. And let me start this off with something we were talking about in 215 yesterday, which is Fibonacci numbers. So if you're in 215 this quarter, this is a rehash of yesterday. So Fibonacci series starts with a pair of 1s, and each number is the sum of the 2 numbers that come before it. I'm really stressing my brain here. And so on. And we can call this F0, F1, F2, and so on. So this is F12 out here. And the series goes on forever. So this pops up in nature, it pops up in mathematics, it describes petals on a sunflower and the way that pine cone things are arranged as you go around the pine cone, and golden ratio and all kinds of things. It's everywhere. And we'll talk about rabbit populations in 215 tomorrow, which is where this was first observed. So we can write code to calculate the nth Fibonacci number, and it's pretty easy. You make a loop. You need to keep track of your 2 previous numbers, and then in each loop you take those 2 numbers, you add them together. That's your next Fibonacci number. And then you just kind of adjust those 2 pointers so that now you're remembering the number you just calculated in the prior one. And the next time through the loop you add those together, and so on. And it usually takes about 3 tries to get the code nailed down. But it's not a complex algorithm. But this is an algorithm that we can use as an example of recursive programming.
Fibonacci numbers and the Fibonacci code, it has something to do with our last programming assignment?
No, dynamic programming is our last assignment, but we're going to introduce dynamic programming with Fibonacci series because it's an easier application. But we'll use dynamic programming to solve something called the Knapsack Problem. That's going to be PA5. And we'll get to the Knapsack Problem a little bit today, but we'll talk about the whole thing in detail tomorrow. All right, so let's write some code. We're going to write a function called fib that takes an integer and returns that Fibonacci number. So fib12 should return the 12th Fibonacci number, which should be 233 if I added correctly. And so I'm just going to have a main program, which is one line. It just prints out fib12 equals, and it'll call fib12. And that's our whole main program. And so I'm going to write a function called fib, which takes an integer and returns an integer. All right, well, we can define this Fibonacci series as follows. So the nth Fibonacci number is either fn minus 1 plus fn minus 2, and that's if n is bigger than or equal to 2. But the first or 0th Fibonacci number, we don't have two numbers before that we can add, so we can define those as just saying the nth Fibonacci number is 1 if n is less than or equal to 1. So f0 is 1, f1 is 1, f2 will be f1 plus f0, f5 will be f4 plus f3, and so on. Okay, so that's a valid mathematical description of fn. It's 1 if n is less than or equal to 1. Otherwise, it's the sum of the two previous values. So we can take that definition of fn and we can turn it into code, and it looks almost exactly the same. So if n is less than or equal to 1, my function is just going to return a 1. Otherwise, it's going to return fib of n minus 1 plus fib of n minus 2. So it's a two-line function. And there's no while loop, there's no temporary variables. I'm using this recursive definition of the nth Fibonacci number, which is it's the sum of the two previous numbers, or it's 1 if n is small. And that's exactly what we've coded in 2 lines of code. So should this work? Yeah, it should. Gotta be able to spell though. So run that, there's the 12th Fibonacci number, 233, which was what we calculated by hand. Okay, so how long did it take me to write these out? Like, I don't know, 30, 40 seconds maybe? So, and that was the first 13 numbers in the series. So if you have a calculator so you can do these additions pretty quickly, it's not that hard to calculate Fibonacci numbers. And if we wanted to calculate the 60th Fibonacci number, we just have to do basically 60 additions. So it might take you a minute to do that, right? Maybe a few minutes. Let's do it on the computer. And we run this, and this is never going to finish.
Might just not in the class ed.
I don't think it's ever going to finish. I think our sun's going to burn out first. Certainly if I do 70, I think that's over the threshold of longevity of the universe. I haven't calculated this recently. So what the heck is it doing? It's got to add 60 numbers together. What is it doing?
It's doing a huge recursive summation.
Yeah, it's doing a huge recursive summation. It's chewing up my stack space. It's getting ready to crash my laptop. And then I got to go buy a new laptop. I actually did this once and my laptop coincidentally died like at that point in class. I ended up buying a new laptop. So I don't actually crash my stack publicly anymore. All right, so let's see what's going on here. Let's just put a print message in here. Let's just print out what it's calculating. So every time that I call fib with a value of n, I'm going to print out the message. I'm calculating fib of whatever that number is. I will go ahead and put a backslash in here. Alright, so here's what it's doing. Alright, it's just like making lots of
It's kind of
calculations.
interesting hitting repeat numbers.
Yeah, it's hitting repeat numbers. So here it did fib of 10. Right? And if I go back up far enough, I don't know how far I'm going to have to go. Here it's doing fib of 10 also. So let's pick something reasonable. Let's do fib of 12. And let's run fib, and it calculated all these values here. Whole bunch of calls to fib.
That's just 12.
That's just with 12. How can we find out how many calls it made?
We can print a running sum.
Could print a running sum.
Like int I equals 0, and every time it goes through, do a +1.
Okay, so we can use an eval global, set it to 0, and every time we call fib, we can add 1 to it. Any easier ways?
If you count the lines,
Hey, let's just count the lines of output. How do we do that?
type it into word count.
Type it into word count. 466 calls to fib, minus 1 where it actually printed the answer. So 400 some recursive calls just to add 12 numbers together. Actually, to add fewer than that, because 0 and 1 are hardwired. Does 466 jump out at you as being special number?
Fibonacci number.
Yeah, it's twice 233, which was fib 12, which is kind of interesting.
That's kind of interesting.
Let's try fib 20. So fib 20 does 21,892 recursive calls. And if I look at the actual value of fib 20, it's 10,946,
That looks like double.
which looks like double the Fibonacci number. So this is kind of interesting. To calculate the nth Fibonacci number, we're actually performing 2n minus 1 recursive calls to the Fibonacci function. So there's some kind of like dual universe here where our numbers have been replaced by a count of recursive calls. That's another topic for another day. So there's a lot of calls going on though, right? So let's do fib of 40. So fib of 40, 40 might be over the limit. Let's do fib of 40. Let's do fib of 30. Because I'm pretty sure for 30 works. Okay, so fib of 30 is 1.3 million.
That was a short fib.
Yeah. And it's
Mine.
2.6 million recursive calls. Alright, so what's going on here? We want to calculate F7. We have to calculate F6 and F5. To calculate F6, we need F5 and F4. To calculate F5, we need F4 and F3. To calculate F4, we need F3 and F2. F3 needs F2 and F1. F2 needs F1 and F0. And to calculate F1 or F0, we don't need to make any recursive calls because those are hardwired. That's that special case in the beginning. But over here to calculate F2, we need F1 and F0. And those are hardwired. And up here to calculate F3, we need F2 and F1, and F2 needs F1 and F0. And over here on this other side, we're going to need to calculate F5. Well, to do that, we're going to need to calculate F4 and F3. And to calculate F4 means all of this stuff. And to calculate F3 means all of this stuff. And we're going to need to do F4 again over here. So how many times are we going to calculate the same value of our Fibonacci function? Right? How many times are we calculating F2?
Hundreds.
Hundreds. And that's why this is so inefficient. Because we keep calculating the same values over and over and over again. So let's take our Fibonacci function and let's search for Fib 5 and see how many times that occurs. We calculate Fib 5 121,000 times. We calculate Fib 2 500,000 times. It doesn't take long, but it takes something because we have to call fib twice with arguments of 1 and 0, have that return 1 in each case, and then do an addition. And fib 5 never changes. It's always the same value. So why not just calculate it once instead of calculating it 121,000 times? So here's an idea, and this is the essence of dynamic programming. Since we know that we're calling this fib function with the value 5 again and again and again, let's calculate it once using this recursive approach, but then let's save the value. And the next time someone asks us for fib 5, instead of doing the recursion, we'll just take that saved value and say, oh yeah, I remember that, fib 5 is 13. And we'll do the same thing for fib 6 and fib 7 and fib 2 and fib 3. So here's the setup for dynamic programming. I'm having issues typing today, so we're going to make an array called save fib. I'm only going to make it big enough to hold 100 numbers. And I'm going to use this to save our calculated values. So every time we calculate a value of fib, we're going to save it in this array. Okay, so how do we use this? So before we make our recursive call, see if we've already calculated this. So if the value in the array at position n is not 0, it means that we've saved a value there from previously calculating this, and we're just going to return that. So we don't have to do any recursion. Otherwise, we've never calculated fib of n before, so we have to actually do this recursive call. So I'm going to save this in a temporary variable. So that might be an expensive thing to do, but once we've done it, we're going to save it. So we'll just save that result into our array at position n. And then we'll just return the result. So we've really added 2 lines of code basically, other than declaring the array. The first line was check to see if we've already saved this value, and if we have, just return it. The second line is if we actually do some calculations, save the result of that calculation in our array for next time. So 2 extra lines of code going to make a huge difference. So there's fib 30, and it turns out we did 60 calls to fib. Fib 50, and it overflows because we've only got 32-bit integers. But it made 100 calls to fib, and it came up with the value of the 50th Fibonacci number. So we're making 100 calls instead of like a few billion calls. That's a big time savings. Alright, so this is dynamic programming. It's basically when you have a situation where you can take your problem and find the solution by solving smaller problems, but you find that in this situation you're solving the same smaller problems again and again and again, right? It's a way to avoid continually recalculating those smaller problems. And in pictures of a tree, this is what we call pruning. So once we calculate the value of f2 and we save it somewhere, we never have to recalculate it. So to find f2 here, we don't have to do all of this. To find f2 here, we don't have to do all this. To find f2 here, we don't have to do that. And in fact, once we find f3, we don't have to do this. And once we find f4, we're not going to have to do any of the stuff that comes under f4. And once we've calculated f5, we're not going to have to do anything on this side of the tree. So this is the term for this is pruning. And it's basically getting rid of pieces of the tree so that the total amount of work you're doing is a lot smaller. And in fact, all we're going to end up doing to find f7 is find f6, 5, 4, 3, 2, 1, and then pop back up. So it's basically 2n. Okay, so this is the concept we're going to use for PA5. But we're going to talk about a number of problems that we can use this for. So PA5 is going to be working with something called the Knapsack Problem. And I'll tell you about the Knapsack Problem right now, and then we'll talk about PA5 details tomorrow. But then after that, we're also going to look at cutting rods. We're going to look at dropping eggs, and we might look at some string manipulation algorithms. And all of these will have this common property. We can solve the problem by solving smaller problems, but we end up solving the smaller problems again and again. So let's look at a general knapsack problem. So you walk into whatever your favorite food co-op is. Do we have any food co-ops in Vancouver? Actually, I don't think we.
I have no idea what a co-op is.
So usually it's owned by like the customers. You have a partial ownership in it, and you might take a turn working there or whatever. But it's like locally grown food, and it's the opposite of the large stores where you go to buy food. And they have a lot of things in bulk. So if you want to buy oatmeal, you don't buy a box of oatmeal from some manufacturer. You go to the oatmeal bin and you scoop out how much oatmeal you want, and they weigh it for you. So picture a place like this, and you're their 1,000th customer, and so they're going to give you a shopping trip for free. So they give you a bag, and this bag can hold, say, 20 pounds worth of stuff. And they say you can put anything you want in here up to 20 pounds. It's yours for free, right? Because we love our customers. So what should you put in this bag to maximize the total value of what you walk out of the store with? And forget that you really like pistachios, and so you're going to fill it with pistachios, right? Just think about pure value. Okay, so different things cost different amounts. Different things weigh different amounts. So salt is very inexpensive. If I were to fill this with 20 pounds of salt, it'd probably be worth like $3. Right? If I was to fill this with pine nuts are very light, and they're also really expensive. 20 pounds of pine nuts, that's going to be a few $100s. Anybody in here cook?
Yeah.
So where does saffron rank on
It's really
price?
Really
It's really expensive. It's probably the most expensive spice commercially available on the planet. So if I could fill this with 20 pounds of saffron, I can retire. I can just open a saffron shop, right? So this is a pretty easy problem, right? Find the value of each item per pound, and whichever one is the most valuable, put as much of that in your bag as you can. If you fill the bag, you're good to go. If you can only find 2 pounds of saffron, you got 18 pounds left. Find the next most valuable thing. Put as much of that in your bag as possible. Okay, so that's an example of what's called a greedy algorithm. A greedy algorithm is one that we can solve by basically trying to solve it as much as possible at each step. And it's greedy, right? So give me the stuff that's valuable to begin with. Let's throw in the gold powder, right? And slowly work our way to the rocks, right? And if there's nothing left but rocks and we got 2 pounds left, we'll take 2 pounds of rocks. So if you can put in fractional amounts of things, greedy algorithm works great for this. Okay, so we're going to complicate this by doing an integral, not a math, calculus integral, but integers, an integer knapsack problem, where you're not allowed to take fractional amounts of things. So imagine that you're at Best Buy and you're their 10 billionth customer, and so they say, okay, you've won a shopping spree, here's a bag, it holds 20 pounds. Put anything you want in there up to 20 pounds, it's yours for free. Okay, well they've got, you know, a laptop that weighs 7 pounds. You could put 2 of those laptops in here, that's 14 pounds. You can't put in 6/7 of a laptop to top it off, right? Because if you break your laptop, it's not worth as much.
Just tear out all the good components.
Get what?
Grab all the good components.
I'll grab all the good components, yeah. So if they have like terabyte micro SD cards, that would be really good, okay? And if they sell, you know, blank notebooks for journaling, that's probably not a good way to fill your 20 pounds, okay, because that's just wood. So the integer knapsack problem, we're going to look at the unbounded version. And so the question is, if they have an infinite supply of everything in their inventory, you can take as many of any items that you want, how should you choose which items to put into this bag to maximize the value? And it may be that, you know, there's a laptop that weighs 19 pounds that's worth $1,000. And you put that in, you got 1 pound left. But there may be these little flash drives that cost $50 each, and you can get way more than $1,000 worth of that in 20 pounds. And so this is a hard problem. It's hard enough that people have used this to create one-way encryption systems, to do like public key ciphers. In fact, there's a version of RSA that's based on solutions to the knapsack problem, because it's hard in the sense of finding prime numbers, and factoring large numbers is hard. But the algorithm is pretty straightforward, right? One way to do this would be to take every possible combination of every item and see how much you end up with and then pick the maximum. But that's combinatorially explosive. But we'll talk about an algorithm that we can use to solve this tomorrow that basically relies on being able to solve this for smaller capacity bags. If I knew what the most was that I could get out of a 19-pound bag, right, I can use that to get a solution to the 20-pound problem. So we're going to work our way towards a recursive solution to this, and then we're going to see that if we try to just code that up with straight recursion, it's going to take forever to run. But if we throw some dynamic programming on it to save our values and pull them back, this will become totally doable. So that's what PA5 is going to be built around. And we'll work on the knapsack problem first, because that's the assignment, but then, like I say, we'll look at some other problems that have similar structure, egg drops, and so on and so forth. So we'll start playing around with that tomorrow. All right, I will see you then.